Hello everyone, I'm Musa, a PhD student at Laval University. I want to talk about our new proposed non-overlapping signal generator, which is a versatile structure for efficient power converters operation. Welcome to my presentation. I organized my speech as you can see here: introduction, proposed VNOSG, circuit implementation, results, performance comparison, and conclusion. A non-overlapping signal generator is an essential building block for a wide variety of systems, including power converters and switched capacitor circuit. An H-bridge as a converter is composed of two half-bridges, each composed of a set of two superimposed complementary power MOSFET switches. This important design is prone to shoot through, which happens when both switches are unintentionally closed at the same time. Shoot-through increases power mass consumption and can potentially damage the switches. This figure shows simplified half-bridge tagged by important parameters. The proposed block receives the master clock from low-power processors and generates two proper signals, Phi1 and Phi2, to drive high-side power MOSFET and low-side 1, LSPM. The half-bridge needs a level shifter, level S, to translate the provided signals for HSPM, in addition to gate drivers for both high and low side, HSGT and LSGT. Usually shoot-through occurs when one MOSFET turns on before or while the other turns off. Thus, a dead-time circuit is used to provide non-overlapping driving signals. Also, shoot-through can happen as a result of the ringing in the driving circuit that causes V gate source to go higher than the threshold. In this case, the damping ratio must be adjusted. In addition, the transient response of the main switching circuit can cause the V gate source of the high side MOSFET to be higher than V threshold. And therefore, the switching frequency or the circuit should be adjusted to handle high dVBDT and dIBDT without crossing V threshold. In this figure, the timing diagram of shoot-through is presented. The repetitive shoot-through current, called IAT, it is clarified how to generate in the unwanted gap of switching delays of high side power MOSFET and low side power MOSFET with an amplitude of IMX. Hence, specific circuit elements are required to ensure a proper and efficient operation, including a non-overlapping signal generator for dead-time control. In the conventional NOSG cross-connected NAND NOR gates and a chain of inverters in the feedback are utilized for generating non-overlapping signals. In this strategy, the NOS is due to propagation delay of the used inverters. This basic configuration generates a delay in the range of several picoseconds, which is not flexible enough to be used in a wide variety of applications, especially for high voltage circuit where longer delay, around millisecond, is needed. As a solution, a versatile non-overlapping signal generator procedure illustrated in the figure is proposed. In this approach, two-sided wide swing current source is used to charge linearly two capacitors, one in each side. Also, three switches in each side are employed to control the charging and discharging process. Finally, two Schmitt triggers with defined comparing hysteresis window in the right and left branch restrict the value of generated delay between the phases. In this circuit, the timing methodology is based on a predefined state machine shown in the right figure. The timing diagram of this technique for generating NOS shows in the left figure. Four states of this machine are CP, CS, CC, and ST, where are acronyms of change polarity, close switch, charge capacitors, and Schmidt triggers, respectively. The left figure shows four curves tagged by TD1, TD2, and different working states. Attained essential benefits by the proposed VNOSG are: first, in this circuit, the generated delay depends on the amount of current delivered by two-sided wide-swinging current source, the value of capacitors, and the comparison levels of Schmidt triggers. Therefore, by adjusting these three parameters, line delay can be obtained, which is needed for high voltage applications that involve large parasitic capacitance and inductance of power MOSFETs. Second, since the operation of this circuit is inspired from a state machine, it is enough flexible to be developed for more complex applications. Finally, the proposed circuit could produce different delays of TD1 and TD2 as the parameters for setting delay in the two phases are independent. For instance, in half-bridge, TD1 and TD2 are the required delay for high side and low side parts. Since the driving signal of high side power MOSFET is passed through more stage, direct shifter, and gate driver than that of the low side part, therefore TD1 is required to be longer than TD2. The transistor implementation of the proposed NOSG for dead time control approach presents here. The two-sided wide-swinging current source is used to provide a wide range of current for the used capacitors. Timing elements consist of Q1 to Q6, C1 and C2, and the controlling signals Phi1 and Phi2 are utilized to generate a ramp signal. For this purpose, among three used transmission gates, for each branch, two of them are responsible to discharge C1 and C2 linearly by avoiding the availability of current source in the input of capacitors. Since the two-sided wide-swinging current source is quickly turning on off, a transition time leads to an added 0.6 volt offset to the generated ramp across capacitors due to the left charge in the output of current source. The third transmission gate for each side, Q1 and Q4, is added to remove the left charge and consequently clean off the offset. The last items of this topology are two Schmidt triggers, which are trustworthy to generate desirable delays if their hysteresis window are set based on the required reference voltage. This figure shows the simulation result for generating short and line delays for high speed and high voltage application, respectively. The minimum generated delay is achieved by putting C1 equal to C2 equal to 2 femtofarad, which are TD1 equal to TD2 equal to 0.01 microsecond. Similarly, maximum generated delay is attained to be TD1 equal to TD2 equal to 0.48 microsecond by utilizing C1 equal to C2 equal to 6 picofarad. This figure shows the half-bridge output waveforms with and without the proposed VNOSG addition. Considerable imperfection when the VNOSG is not employed are highlighted in the top waveform numerically. While after adding VNOSG, repetitive shoot-through is totally removed in the bottom waveform. This figure shows the micrograph of designed tape-out implementation in 0.35 micrometer technology. It consists of high and low side power MOSFET, HSPM and LSPM, high and low side gate driver, HSGD and LSGD, level shifter, some dummy capacitors for compensating metal density, and VNOSG black. The VNOSG including two-sided biased current source, Schmitt triggers, capacitors, and transmission gates occupies only 180 micrometer cross 70 micrometer. The post-load simulation result demonstrates the important curves, including phase 1, phase 2, and ramp signal across one of the main capacitors. The substantial parameters are TD1 equal to 33.5 nanosecond. Remove the 0.6 volt offset from ramp signal by adding third transmission gate, and high and low Schmitt trigger comparison levels. To analyze the circuit operation based on this figure, the generated delays between phases depends on the slope of ramp signal, and the Schmitt trigger hysteresis window would be changed. For example, if the value of capacitor is increased, the slope of ramp signal will be decreased, resulting in VRF2 that meets the ramp signal in the later time. Consequently, the TD1 will be increased. The performance comparison of the proposed VNOSG with the recent circuits are presented here. In this work, TD1 equal to KTM as an important parameter which considers the versatility of a circuit is significantly better than the others. In this parameter, Tm is defined as a master clock period. Besides, the other parameters are comparable with similar recently published systems. It should be noticed that previous methods generated various delays with different master clock period. The versatility parameters of compared methods are presented in the proportion of their master clock period. In this way, the achievements of method are sufficiently comparative. As a conclusion, we proposed a new flexible interface to generate non-overlapping signals for switch capacitors and power converters. The traditional non-overlapping signal generator method utilized the logic gates and inverters to create a delay, while the proposed approach named VNOSG employed timing elements, combination of capacitors and current source. The privilege of the proposed method is that the output signals are delay adjustable, flexible in developing, and parameters independent from each other. Finally, I would like to thank you for your attention. If you have any question, I am pleased to answer.